All right. Hello, everyone. I just saw you in class, but welcome back again. I hope you had a great vacation. I'm actually filming this before a vacation, so I'm hoping I had a good one too. Anyway, nice short lesson for you today. We will have just finished up in class a big, gigantic review of confidence intervals and hypothesis tests for proportions and for difference of proportions. So that was the plan for in class, just to kind of remind you what we're doing. We're going to continue with the hypothesis test, but now we're doing and confidence intervals, but now we do it for a mean instead of a proportion. Okay, so in other words, let's say I wanted to find a confidence interval for the mean test score or a GPA at Mountview High School or something like that. So just a different test statistic. Instead of looking at a yes or no, success or fail question, we're going to look at a data and a mean. So today's lesson is pretty quick. It's going to look and feel very similar. The formula is going to look and feel almost exactly the same because they are. Just use a different standard error is all. So confidence interval for a mean is what we're going to do. Typically, I put in there confidence interval for a mean with a normal population and standard deviation of the population known. The normal population part we don't have to have. I'll talk about it in just a second. But for now, we need to know the population standard deviation. This is a little weird because normally we would never know that. So mathematically, we need to use that number right now. Ultimately, we're going to move away from that and show you how to do it when we don't know it. But we're going to teach you the math first, and then we'll go to that second. So confidence interval for a mean is exactly the same as the confidence interval for a proportion, set up the same way. So remember, proportion, real quick here, was p hat plus or minus z star times the square root of p hat q hat over n. And this is what's called standard error, right? Every confidence interval is built this way. So it's the same thing. So we start with x bar. That's our sample average, is x bar, plus or minus our critical values, found the same way it was for the proportion, and then standard deviation of the population divided by the square root of n. This is also called standard error, but it's standard error for a mean, right? So this is standard error for a mean, and this is standard error for a proportion. All these formulas are on your note sheet, by the way, also. So that's it. I'm going to do an example here in just a second. It's got some conditions. Conditions are down here, and then we'll do a little couple example problems. The conditions, just like every other problem, simple random sample. So remember the next condition for the proportion would have been NP hat, NQ hat greater than or equal to 10. The idea there is we need a big enough sample size for our sample distribution to look normal. Okay, so same thing goes here. We've done this before, but it's been a while. The condition for the sample size being big enough for this one is greater than or equal to 30. Okay, because we don't have a p hat, right? So it's a little bit different, but it's the same idea. It has to be big enough. However, if you start with a normal population, this doesn't matter. So either you have to have a normal population or your sample size needs to be big enough. All right. For the proportion, we don't have the condition for a normal population because there's no such thing as a normal population where there's only two outcomes. But for the average, it could be normally. And then the third condition is just like it's been for everything else. The population is at least 10 times the sample size. Okay. So let me just show you an example. Here's an example. We take a simple random sample of 9 SAT scores with a standard deviation of 150. The sample mean that we get from those 9 scores is 110. Find a 90% confidence interval. So normally I would write in the problem, I just shortcutted this. They would tell you that the population is roughly normal. Okay, so the SAT scores are roughly normal. So the way we build the confidence interval is very simple. It's 110. That's my average. 110 for SAT scores. Maybe this is something else. I don't know. Maybe it's supposed to be 1100 or something like that. Oh yeah, that's bad. Let's change it to 1110 because since we got a standard deviation of 150, that's pretty big. So we're going to go 1110 plus or minus the critical value. So the 90% critical value, you may remember, is 1.645. If you forget this, remember it's 90%, which leaves 5% on each side. So you would do it just like normal, an inverse norm of 0.05. And then it's the standard deviation of the population, which is 150 divided by the square root of the sample size. So we multiply this out, 1.645 times 150 divided by 3. So it's 1110 plus or minus 82.25. So then if I write this up as an interval, which is probably the best way, 110 minus 82.25 is 1027.75 to 1110 plus 82.25, 1192.25. And then remember interpretation of the confidence interval. I am 95% sure that the actual average SAT score is somewhere between 1027.75 and 1192.25. Going to look and feel, as we go through chapter 9, it's going to look and feel exactly like proportions. I hope that's the idea. So just some new formulas and that sort of thing. But the way we write it's going to be the same. The way we test it's going to be the same. The answer to these other kind of questions are going to be the same. The next one is you form a confidence interval that's too big, right? So a lot of times you get it too big. How do you make it shorter? There's two ways to make it shorter. Remember, the more confident you are, the bigger the interval becomes. So remember, you have control over two things in your formula. So let's go back here to the formula. You have control over your z star. So if that's too big, we just make that smaller, which means we make the confidence level smaller, right? So that's one way. The other way, think about this. If n gets bigger, this number gets smaller. So that whole margin of error becomes smaller. So the answer to this question would be smaller confidence level always makes it smaller, or bigger sample size. Now we talked about that. Nothing's different than that what we did with proportions also. And then the last question is finding that sample size, just like we did for proportions. So if we have a standard deviation of 10, how big a sample size do we need to have a 95% confidence interval with less than 1? So remember again, come down here, my margin of error formula is z star times standard deviation of the square root of n, right? So how big a sample size do I need to be within 1? So my margin of error would be 1. 95%, 1.96. Standard deviation of the population was 10 over the square root of n. So remember, it's just an algebra problem like we've set up before. So I'll walk you through the steps. 1 divided by 1.96 is roughly 0.51 equals 10 over root n. I'm going to flip-flop these places. So root n equals, and I'm not going to round that number right now. It's just sitting on my calculator. I'm going to go 10 divided by that number, 19.6. And then I'm going to square that number, and I get 384.16, which means I need to get up to 385 to get within 1. So like I said, you're going to see a lot of similarities, a lot of the same sort of stuff we did for proportions. The next section will be the hypothesis test for this, I think. I guess we'll find out soon enough. So I'll see you in class tomorrow.